A single point of light is leaving the solar system. At first, it doesn't look unusual. One observation places it here. A few hours later, another places it farther out. Then another extends the same path. The object never stops, never turns back. Against the background of distant stars, it's nothing more than a faint, moving dot. But the orbit tells a very different story. Lay the first observations beside the latest calculations. Newly discovered objects almost always begin with uncertain paths. Give astronomers a few more nights, and those paths usually settle into something familiar. An asteroid closes into a long ellipse. A comet traces another predictable loop around the sun. This one refuses. Every new measurement pushes the orbit farther outward. Instead of closing, the path stays open. Astronomers run the numbers again. Then again. Other observatories join in. Different telescopes, different teams, different software. The answer doesn't change. One number explains why. The object's orbital eccentricity is about 1.2. Every asteroid and every comet that belongs to the solar system stays below 1. Cross that boundary, and the sun can still bend your path. It just can't keep you. This object was never captured. It arrived already moving too fast to belong here. Look back at the point of light. It hasn't changed at all. No telescope can reveal its surface. No camera sees more than a dim speck reflecting sunlight. Only its meaning has changed. Astronomers are no longer following another small body orbiting the sun. They're watching the first confirmed interstellar visitor ever observed. Oumuamua. The International Astronomical Union even creates a new class of object for it. Not because the discovery demands a new idea, but because the evidence no longer fits the old categories. For decades, scientists expected something like this to exist. Young planetary systems are chaotic places. Giant planets can fling rocks and ice completely free of their parent stars. Over millions of years, those fragments should drift through interstellar space. The prediction had always made sense. What nobody had was proof. Now the proof is crossing our solar system. Bring back the orbital map. The planets continue along the same familiar paths. Known comets disappear into deep space, then return years later. Only one trajectory refuses the pattern. It arrives from the darkness between the stars, bends once around the sun, and opens back into interstellar space. One mystery is already gone. The object doesn't belong here. But solving that mystery creates a harder one. An orbit can tell astronomers where an object is not from. It can't tell them where it is from. It can't identify the planetary system that launched it. It can't reveal what happened before the journey began. The point of light keeps moving away. Somewhere inside that tiny traveler is the first physical evidence humanity has ever received from another stellar system. The challenge is no longer proving where it came from. The challenge is discovering how much of its forgotten home it still carries. The obvious place to start is with the simplest idea. If Oumuamua came from another planetary system, maybe it's just another asteroid, a familiar object with an unfamiliar birthplace. At first, The evidence seems happy with that explanation. Its trajectory explains why it appears only once. Planetary systems should be throwing countless fragments into interstellar space. Most will wander forever between the stars. Every so often, one should pass close enough to another sun to be seen. Oumuamua could simply be the first one we happened to notice. Nothing more. The investigation shifts from motion to light. No telescope can resolve the object itself. It's far too small and far too distant. Instead, astronomers measure something much simpler. How much sunlight reaches Earth as the object turns? Another observation comes in. The visitor grows brighter. Hours later, it fades. Then it brightens again. The pattern repeats. Plot those measurements on a graph, and the brightness rises and falls in a steady rhythm. One full cycle takes a little under 8 hours. The object is rotating, exposing different surfaces to the sun before turning them away again. Independent observatories record the same signal from different skies with different instruments. The rhythm survives every test. The first reconstruction almost builds itself. Picture a long, rocky fragment spinning through space. When its broadside faces Earth, it reflects more sunlight. Turn it again, and only the narrow edge remains visible. The brightness drops. Keep spinning, and the same cycle repeats. Computer models reproduce much of what the telescopes see. Some suggest Oumuamua may be at least 5 times longer than it is wide. Others push that ratio even higher. Whatever the exact number, the object appears far more elongated than almost any asteroid we've observed inside the solar system. For a moment, everything fits. The orbit explains why it's here only once. The changing light explains the flashes. Its unusual shape explains the changing light. The picture feels complete. An ordinary rocky object. An extraordinary journey. Then the pattern starts slipping. The brightness still rises and falls. But the timing drifts. One rotation no longer matches the next as cleanly as a simple spinning body should. The difference is small. The overall rhythm survives. Yet, it never becomes perfectly predictable. Astronomers check the data again. The measurements hold. So does the original model. Just not comfortably. Oumuamua is almost certainly rotating. It just may not be rotating the way anyone expected. The first reconstruction still explains most of the evidence. For the first time, though, one stubborn observation refuses to fit. That tiny mismatch will eventually become one of the most important clues in the entire investigation. Hold the light curve beside the rotating model one more time. The overall pattern is still there. Oumuamua continues to brighten and fade as it tumbles through sunlight. But the brightest moments refuse to arrive on a perfectly regular schedule. A simple spin should keep nearly perfect time. This object doesn't. The difference is subtle. It's also persistent. As more observations arrive, astronomers test another possibility. Maybe Oumuamua isn't rotating around a single stable axis at all. Maybe it's tumbling, rolling through space while spinning at the same time. An object thrown violently out of a distant planetary system could keep that chaotic motion for millions of years, if nothing ever slowed it down. The new model immediately explains something the first one couldn't. The brightness still repeats. The timing never quite does. Look back at the graph. Nothing on it has changed. Only the interpretation. What first looked like evidence for an unusually long object is now revealing something else as well. The changing light isn't describing shape alone. It's describing motion. That shifts the investigation again. Astronomers are no longer asking only what the visitor looks like. They're asking what kind of journey leaves an object spinning like this for millions of years between the stars. Every measurement now carries two stories at once. One about the object itself. The other about the planetary system that expelled it. A completely different set of observations soon begins drawing attention. This time, the clue isn't hidden in changing brightness. It's hidden in changing position. Night after night, observatories record exactly where Oumuamua appears against the background stars. Those positions are compared with the path predicted by gravity alone. At first, they almost overlap. The difference is barely visible. Then it grows. Not by thousands of kilometers. Not even hundreds. Just a tiny amount. Small enough to dismiss. Too consistent to ignore. Night after night, the object appears slightly farther along its path than gravity alone predicts. The measurements are checked. Independent observatories reach the same result. The discrepancy survives. By itself, it isn't enough to overturn anything. Tiny errors are common when tracking a faint object that's rapidly disappearing into deep space. The easiest explanation is that more observations will smooth the difference away. Instead, the opposite happens. As new data are added, the gap refuses to shrink. Oumuamua is no longer challenging the first model of its shape. Now it's beginning to challenge the first model of its motion. Something, however slight, appears to be giving the object an extra push as it leaves the solar system. Gravity may not be telling the whole story. The simplest explanation is suddenly under pressure from two directions. The object seems to be tumbling. Its trajectory is drifting. Either observation could still have an ordinary explanation. An unusually shaped body can tumble. Small measurement errors can shift a calculated orbit. Together, those explanations become harder to believe. Astronomers continue comparing the observed positions with the path predicted by gravity. The mismatch grows slowly, but it grows consistently. Oumuamua is moving away from the sun just a little faster than gravity says it should. The effect is tiny, yet it appears in independent observations collected over many months. Eventually, the signal survives every statistical test. The extra acceleration is real. A familiar explanation immediately moves to the front. Maybe Oumuamua isn't an asteroid at all. Maybe it's an ordinary comet. Comets don't travel under gravity alone. As sunlight warms their icy surfaces, escaping gas acts like a gentle rocket engine. The push is weak, but astronomers have measured it countless times. Better still, the direction matches the acceleration seen here. For a brief moment, the puzzle seems solved. if invisible gas is escaping from Oumuamua, the strange motion no longer needs a strange explanation. The next observations should make that obvious. Astronomers search for the usual signs of comet activity. A cloud of gas around the object. Dust streaming away from its surface. Infrared fingerprints left behind as frozen material evaporates in sunlight. Nothing appears. No cloud. No dust. No detectable gas. Even with increasingly sensitive observations, Oumuamua remains nothing more than a bare point of reflected sunlight. Its motion behaves like a comet. Its appearance does not hold that same image again. The object hasn't changed. It's still a tiny moving point. Only the story attached to it keeps changing. First, it looked like another asteroid. Then an unusually shaped visitor from another star. Now even the simplest comet model begins to crack. Gravity alone can't explain every observation. Neither can an ordinary comet. The evidence isn't contradicting itself. It's narrowing the possibilities. Whatever Oumuamua is, it carries a history unlike anything humanity has ever watched pass through the solar system. The question is no longer whether the first model survives. It doesn't. The only question left is which explanation can account for every measurement without asking any of them to disappear. By now, the investigation is no longer searching for a perfect answer. It's searching for the explanation that leaves the fewest contradictions behind. Every reliable observation is now on the table. Oumuamua follows an interstellar trajectory. Its changing brightness points to an unusually elongated, or perhaps flattened, body. Its complex rotation hints at a violent past. Its path departs slightly from gravity alone. At the same time, every familiar sign of an active comet remains absent. No single observation explains the others. Together, they begin drawing surprisingly tight boundaries around what this object could be. The question slowly changes. Instead of asking what Oumuamua is, astronomers begin asking what kind of planetary system could have produced it. Several ideas survive. One proposes that the visitor was once rich and exotic frozen material. Material capable of producing a gentle push without creating the bright dust cloud expected from an ordinary comet. Another imagines a fragment blasted from the frozen surface of a distant world during a catastrophic collision. Others point toward the violent early years of planetary systems, when giant planets scatter smaller bodies into interstellar space. The details are different. The standard is not. Every proposal faces the same evidence. It has to explain the orbit. It has to match the changing brightness. It has to remain consistent with the complex rotation. And it has to account for the small outward acceleration without producing the visible coma astronomers never observed. Fail one of those tests, and the model begins to lose support. No matter how appealing it first seemed, the investigation starts to resemble forensic science more than astronomy. No one witnessed the event that launched Oumuamua. Its parent planetary system has never been seen. The collision, close encounter, or gravitational ejection that sent it away happened long before humanity existed. Only one piece of evidence survived: the traveler itself. Like a fossil preserving traces of an ancient ecosystem, Oumuamua preserves physical clues from a planetary system no telescope has ever observed directly. Some questions can still be answered. The object almost certainly formed around another star. Powerful gravitational forces eventually threw it into interstellar space. It survived an immense journey across the galaxy before passing through our solar system. Other questions remain beyond the reach of the evidence. No measurement can identify one specific parent star. No observation can reconstruct the full history of its voyage between the stars. Those details left with the object, and they may never return. Even so, the investigation achieves something remarkable. Without leaving the solar system, astronomers reconstruct part of the history of an unseen planetary system using nothing more than the evidence preserved inside one passing object. The reconstruction is incomplete, but it's also the strongest picture the evidence allows. The point of light continues moving away from the sun. It's now so distant that no telescope can follow it any longer. The visitor has faded beyond direct observation. No sharper image is coming. No future measurement will recover information that was never collected. Oumuamua continues exactly as it did before humanity noticed it. The only thing that changed was us. Return to the orbital map. The planets are exactly where they always were. Earth continues around the sun. Jupiter follows its familiar path. Nothing on the map has moved, except our understanding of one line. At the beginning, it was simply an unusual orbit. Now it's the only surviving record of a planetary system humanity has never seen. Everything scientists can say about that distant system comes from the brief passage of one silent traveler. Its trajectory proved another star had once lost part of its own planetary system. Its changing light preserved clues about its shape and motion. Its final measurements placed firm limits on what could and could not be reconstructed. Oumuamua never told us its story. It only carried enough evidence for us to recover a small piece of it. Some questions will remain unanswered. Not because the investigation ended too early. Not because a better theory is waiting. Because the remaining evidence is no longer here. The visitor is still carrying it through the darkness between the stars. Hold the point of light one last time. It looks exactly as it did when this story began. A tiny moving dot. Nothing more. And yet, it is no longer just a visitor. It is the first physical reminder that our solar system is not alone. Sometimes, another world passes quietly through ours. Then it is gone. The point of light keeps moving. Its meaning stays behind.